Hello, my name is Erik de Haye, and today I will be giving you a short presentation on inflation with a particular focus on slow roll inflation. Throughout the presentation I will be using natural units and an FLRW metric. I will also be using these relations for the Hubble parameter, which follow from the Einstein equations. In this case, rho is the energy density and P is the pressure of the inflaton field, which I will introduce now. The inflaton field is assumed to be a homogeneous scalar field phi, which evolves in a potential V. The energy density and pressure are given by these relations, which follow from the stress energy tensor, and plugging them into the aforementioned relations for the Hubble parameter will yield these equations. In the following, I will also be using the Klein-Gordon equation, which gives the evolution of the field. It consists of an acceleration term on the left, potential gradient term on the right, and then a Hubble damping term which comes from the expansion of the universe. For slow roll inflation, the following approximations have to be made. Firstly, that the potential dominates over the variation of the field squared, and that the Hubble damping term dominates over the acceleration of the field. Plugging these approximations into the previously mentioned equations of motion reveal the approximation for the equations of motion. These approximations can be parameterized by a few slow roll parameters. I will be choosing epsilon1 and epsilon2 given by minus h dot over h squared and epsilon1 dot over h epsilon1. As long as epsilon1 is far smaller than 1, the approximation that the potential dominates over phi dot squared is valid, and as long as the absolute value of epsilon2 is far smaller than 1, the approximation that the Hubble damping term dominates over the acceleration of the field is valid. So the first parameter being small ensures a slow variation of phi, while the second parameter being small ensures that the slow variation holds over a long period of time. And this then results in a Hubble parameter which is almost constant and thus an almost exponential growth of the scale factor. And this in turn can explain multiple observations. I will be going into detail on one of those, which is structures on super Hubble scales. In the sketch, the red line shows the structure of a given physical wavelength lambda, which grows with the scale factor A, and the dashed blue line shows the Hubble length, which relates to the causal horizon and is constant during inflation and grows with a to the fourth and a to the third power during radiation domination and matter domination respectively. A structure of a given wavelength lambda, which is formed either before or in the beginning of inflation, can grow beyond the Hubble length, making it super Hubble. Then later, during radiation domination or matter domination, it can cross back across the Hubble length, making it visible to an observer. So without inflation, there's no apparent reason why structures on super Hubble scales should exist, and inflation explains that these structures were formed in the early universe and then only crossed into the super Hubble regime because of inflation. That concludes this short presentation. Thank you for watching, and goodbye.